In this video, I will be writing down the energy balance for a flow system and then deriving the Bernoulli equation as it arises from the energy balance. So the first thing I want to do, I want to state how much energy our system has. All right, so the energy of a system is the mass of the system times internal energy per unit mass plus kinetic energy per unit mass plus potential energy per unit mass. Right? And for our energy balance, we want the energy or the change in energy of the system to be equal to any energy coming in, right? Any energy being added minus any energy being removed. Right? So we want a differential change in this energy of the system. Right? And we will set this equal to a differential change in mass coming in times internal energy plus kinetic energy plus potential energy per unit mass. Let me write this 2 better. Minus the differential change in mass coming out times internal energy plus kinetic energy plus potential energy coming out of the system. So that would be, if we had our system here, we had a mass coming in and a mass coming out. This mass right here will have an internal energy, kinetic energy, and potential that it's bringing into the system. This mass will have the same that it is bringing out. Right. Another thing we can do is we can add heat to the system. So plus dq, and we can do work on the system. Right. So if we had like a stirrer here or a compression, those would be types of work. But more specifically, those are non-flow work. What we want to do is separate these non-flow work from our flow work. Right. So we have our work done by the flow of the system, and that is equal to the volume, the change in volume. Oops, not change in work. Our change in volume coming in times the pressure coming in minus change in volume going out times pressure going out. And so now what we want to do is we want to actually write these in terms of a change in mass, right? So if we look at volume, that's meters cubed. If we multiply volume by density, which is kilograms per meter cubed, we get our mass. Now taking the derivative with respect to mass, we get dm, right? The change in mass equals density times the change in volume. Now, dividing by density on both sides, we get that the change in volume equals change in mass over density. Now we can substitute that in. So our flow work equals pressure in over density in times some differential amount of mass coming into the system minus pressure out over density out times some differential change in mass coming out of the system. Right. And now if we look here, we have our change in masses, and we can actually just write those into our equations here. Right. So if we have plus pressure over density on both of these, oops. Coming out. All right. So now we've added our flow work into this top part here, which means that we can't use just our change in energy brought about by work here. We need to write specifically our non-flow work. Okay? So now I'm going to clear this up a little bit. All right. So now the next step, if we look at enthalpy, enthalpy equals internal energy, all of these are per unit mass, plus pressure times the specific volume, right? Because this volume per unit mass ends up being our meters cubed per kilogram, right? So if I write that equals 1 over density. And now if we look here, right, if we substitute that in, enthalpy per unit mass equals internal energy per unit mass plus pressure over density. If we look in this equation up here, right, we already have enthalpy plus pressure over density. So we can substitute those guys. Right, erase that thing. All right, now we have enthalpy. And so our final energy balance for a flow system states that the change in mass, the change in energy of a system can be brought about by a change in mass coming into the system multiplied by its enthalpy per unit mass plus kinetic energy per unit mass plus potential energy per unit mass. I actually want to write G and not P here. GZ, right? Minus some differential change in mass coming out of the system times its own enthalpy per unit mass plus kinetic energy per unit mass plus potential energy per unit mass plus any heat we add to the system plus any non-flow work we add or we perform on the system. Right, and so now I will be doing an example with this. Right, so we have what we want to do is calculate the temperature increase of water arising from constant velocity and potential energy with a pressure drop of 900,000 pascals. All right, so if we look here, the first thing we notice, constant velocity and potential energy means that those two terms cancel out. We have no heat and no non-flow work. But something else that we can say about constant velocity is that the mass coming into the system is the same as the mass coming out of the system, right? So this change in mass of the system is 0, which means that the change in energy of the system is 0, right? So we have 0 equals some differential amount of mass coming in times enthalpy going in minus the differential change in mass going out minus enthalpy out. But again, the mass coming in and the mass going out are the same, which means that these terms cancel out, and we are left with enthalpy in minus enthalpy out equals 0. So the enthalpy going in equals the enthalpy going out. Now the next step, if we look at enthalpy again, enthalpy equals internal energy plus pressure over density. So we have here internal energy going in plus pressure in over density in equals internal energy out plus pressure out over density out. And now I will bring like terms to both sides. And so on the left side, we will have pressure in minus pressure out over density. Right? So we can use a common denominator of just density here because we have water coming in and going out. So the density of both of those will be the same. And that is equal to the internal energy out minus internal energy in. Right. And as I stated in an earlier video, the internal energy is a proxy for temperature, right? So internal energy equals CV, our heat capacity with constant volume times temperature. Right? So now I will write pressure in minus pressure out over density equals CV, T out minus T in. And once again, we can take the heat capacity out because for both sides it is water, so the heat capacity is the same. So we don't have to worry about heat capacity going in, heat capacity coming out. And now it's just a little bit of calculation here, right? So the pressure drop of 900,000 pascals means that our pressure going into the system is 900,000 pascals more than the pressure coming out. So 900,000 over our density of water. Density of water is 1,000 kilograms per meter cubed equals heat capacity of water, which is 4,186 joules per kilogram Kelvin, times our temperature out minus our temperature in. Right. So now if we look at this, calculating that, we get that 0.215 equals our temperature out minus temperature in. So the temperature increase of the water arising from this flow is going to be 0.215 Kelvin. Right. And now I will be moving on and deriving the terms of the Bernoulli equation. Okay, so for the Bernoulli equation, we have that it is a steady state equilibrium, right? So that means that the mass going into the system equals the mass coming out, right? So for Bernoulli, mass going in equals mass going out, which also means that the change in mass of this system equals 0. Right. So 0 equals, and we can just write dm, right? The change in mass of our enthalpy going in minus our enthalpy out plus kinetic energy in, or so we will have our velocity in squared minus velocity out squared over 2 plus g times z in minus z out. And what I actually want to do here is I don't want enthalpy, I want our internal energy plus pressure over density. So I will write that in here. So pressure in minus pressure out. And another factor or another part of the Bernoulli equation is that it is incompressible, which means that the density going in equals the density going out. So we have this common denominator here, which is just density. Right? And then we have our heat added and our non-flow work. So plus dq plus non-flow work. The next step, I'm going to divide by this differential change in mass and subtract these three terms and bring them to the other side. Right, so we have velocity out squared minus velocity in squared plus gravity times z out minus z in plus pressure out minus pressure in over density equals our first our internal energy in minus internal energy out plus change in heat or change of mass plus our non-flow work over our change in mass, right? And so now this term right here this is considered our frictional heating. And this side is actually our Bernoulli equation. Bernoulli equation. And that it's the Bernoulli equation when it is set equal to 0. Right. So now the Bernoulli equation means that there is no frictional heating and there's no non-flow work. So we just have a 0 there. Right. So now I will be solving a problem with this. I'm going to clear up the board a little bit with everything. Okay, so now I will be calculating the velocity of air arising from a pressure drop of 10,000 pascals. So if we imagine we have some container and there's some velocity out, right? We have our pressure inside is 10,000 pascals, right? It's 10,000 pascals, 10 to the fourth, greater than the outside, right? So because we have pressure out minus pressure in, we can just write these as relative terms. Right? So we have instead of having like 10 to the fourth plus 101,325 and 101,325 here, we can just write 10 to the fourth, right? So now, this is over 2. This velocity squared coming out minus velocity in squared is over 2, right? Okay, so we have a pressure drop of 10,000. We do not have any change in potential energy, right? So we can write this as velocity squared going out minus velocity in squared over 2 plus pressure out minus pressure in over density equals 0. Now subtracting this to the other side and multiplying by 2, we have v squared out minus v in squared equals 2 times the pressure in minus pressure out over density. All right. Now, in this case, we don't actually have any velocity going into the system. So this term we can just take out, right? That is equal to 0. And now we need to calculate the density of air. Right, so if we look at density, right, density is some mass per volume, right? And the mass of air would be the number of moles times the molar mass. We can set that over volume for our density. Now if we look at our ideal gas law, let me write this a little better. V equals nRT. If we solve for n over v equals P over RT. Right, so now we can say that density equals pressure over, or pressure times molar mass over R times T. Right. So now we actually need to calculate molar mass. Right. So the molar mass equals, it is a mass over the number of moles. Right, so we have the number of moles. And the air is approximately 79% nitrogen. So 0.79 times N times 28, which is the molar mass of nitrogen, and about 21% oxygen. Right? It is about 20% oxygen. It's about like 1% argon, but we are just going to say oxygen here. So plus 0.21 times 32, right? So now 0.21 N plus 32. So now we can see this this n here, these n's all cancel out. We get that the molar mass of air is approximately 29. So now bringing this 29 grams per mole over, right, we have the pressure, which we will say this is in atmospheric conditions, right, standard atmosphere. So 101,325 times 0.029, right, because we want kilograms and not grams, over R, which is 8.314 joules per mole Kelvin, times our temperature, which is 298 Kelvin at atmospheric conditions. And this is equal to 1.2 kilograms per meter cubed. Just about. Right, now plugging this into our equation down here. Right, we have our density, we have our pressure difference. So 2 times 10,000 over 1.2. So here. If we take the square root of both sides, we have the velocity going out of the system equals the square root of 20,000 over 1.2, which is approximately, we'll say, approximately 129 meters per second. And that is all for now. Thank you.